You've probably had ants bother you at least once, invading the cake you left on the table, or swarming over the unsealed jar of honey. These little creatures can be annoying, but consider yourself lucky you live in the 21st century, where a spray bottle is all you need to repel them. If you could go back in time 50 million years, things would be completely reversed. You would be the underdog. In the humid forests of the Eocene, there lived a species of giant ant, nearly as long as a human finger, with a wingspan as wide as a hand, that hunted down anything that dared to get in its way. That was Titanomyrma, the giant ant that once ruled the Earth. And its story is not just about power, but also about how Earth opened temporary climate gates that allowed life to migrate between two continents. Today, let's explore how could a tropical creature cross the icy Arctic of 50 million years ago. Part 1. Myths, fact the legend of oxygen. From classic creature features to modern blockbusters, we've long been fascinated by the idea of giant insects. And the explanation we most often hear, that prehistoric air was richer in oxygen. Cut to vivid CGI, we're now in the Carboniferous period, 300 million years ago. A massive dragonfly, Meganeura, with a wingspan of 70 centimeters, 28 inches darts through a dense forest of towering ferns. A GFX chart fades in, showing atmospheric oxygen peaking above 30%, rising in tandem with insect body size. At first glance, the theory seems perfectly logical. During the Carboniferous and Permian eras, when oxygen reached its highest levels, the largest insects in Earth's history appeared. Insects lack lungs. Instead, they breathe through a network of narrow tubes called tracheae. A more oxygen-rich atmosphere would have allowed the system to deliver oxygen deeper into their bodies, theoretically, enabling far greater size. It's a neat, elegant story, almost too neat. But science, like a good detective, never stops at the first explanation. And when researchers at the University of California, Santa Cruz took a closer look, they uncovered a clue that flipped the whole story on its head. Here's the turning point. Around 150 million years ago, that neat correlation broke down. A comprehensive study of more than 10500 insect fossils revealed that even as oxygen levels rose, insect size began to shrink. The culprit wasn't chemical, it was biological. A new predator had taken to the skies: birds. The evolutionary pressure had shifted. The arms race in the air was no longer about who could grow the largest, but who could dodge best. Agility became more valuable than size. The sky had become a dangerous place, and being a large, slow target was no longer a recipe for survival. So what then produced Titanomyrma in the Eocene, long after birds had already claimed the air? The answer lay not in the air they breathed, but in the world they inhabited. Not an oxygen-rich world, but a greenhouse world, where global temperatures soared to extremes. The key wasn't oxygen, it was hyperthermal's brief, yet intense global warming events. But how could a heat-loving creature possibly thrive so far north in ancient North America? In our modern world, ants are a familiar, often annoying part of daily life. We think we know them. But 50 million years ago, there was one species you couldn't simply brush aside. Meet our protagonist. Not a monster, a queen. The queen ant Titanomyrma gigantea, the largest ant species ever discovered. At nearly the length of a grown man's index finger and a wingspan wider than a human hand, she was a true giant among insects. Her size eclipsed even the queens of today's largest species, the fearsome African driver ants Dorylus, already terrifying in their own right. Naturally, the first question people ask is, did it sting? Fortunately, fossil analysis shows that it lacked a stinger. But don't breathe easy just yet. It wielded another weapon, one that would feel familiar to anyone who's seen animated ant movies. Like many modern ants, its defense was likely formic acid sprayed from its abdomen to subdue prey or repel attackers, a chemical weapon rather than a physical one. Scientists distinguished the species within the Titanomyrma genus mainly by the shape of their abdomens. The European T. gigantea had an oval-shaped abdomen, while the American Titanomyrma lubae had a noticeably more elongated one. This subtle difference, combined with the fossil's discovery site, told an extraordinary story, one fossil in America that redrew the entire map of the ant world. Part 2. The Giant Queen and the Wyoming Case. Our story begins here inside an ancient lake known as Fossil Lake. 50 million years ago, this wasn't a semi-desert, but a lush, subtropical ecosystem, perhaps much like today's Florida Everglades. Its warm, calcium-rich waters created near-perfect conditions for preservation. Anything that sank to the bottom, leaves, crocodiles, bats, insects, was sealed in fine powdery sediment, forming a natural coffin for eternity. Sometimes, the greatest discoveries don't emerge from dramatic excavations, but from a dusty museum drawer. like finding a lost Rembrandt painting at a flea market. For years, the fossil lay unnoticed in a museum collection found and donated by an amateur collector named Louis Loeb. It wasn't until Dr. Bruce Archibald of Simon Fraser University and then curator Kirk Johnson stumbled upon it that its true importance came to light. This was the first complete specimen of a giant ant ever found in the Western Hemisphere. Until then, the only evidence of this ant family in North America had been a single, isolated wing fragment discovered in Tennessee. The Wyoming find was a shock. It posed a puzzling question. What was a heat-loving ant, whose closest relatives lived in Germany, doing in the middle of North America? Did they fly there? Unlikely not across a vast ocean. Drift on rafts of vegetation, possible but improbable. Or did they walk? That was the most logical answer, but it required a land bridge. And in the Eocene epoch, the only land bridge connecting Europe and North America lay in the most unlikely place of all, the Arctic. When we picture the Arctic, we imagine a frozen wasteland, an impenetrable barrier to most life. But the past is another country, and the Arctic of 50 million years ago would have astonished us. At that time, continental drift had not yet fully separated North America from Europe. Land bridges still existed, forming corridors across an ice-free Arctic. Scientists call them the de Geer route in the north and the Thulian route in the south. For most of the time, the Arctic's climate was temperate, mild winters, but still too cold for tropical species. It was like a bridge with a gate. Many cool-adapted plants and animals could cross freely, but for heat-loving creatures like Titanomyrma, that gate was shut. Imagine an intercontinental highway that opens for only a few days every century. You have to catch the right window, or you're trapped. For Titanomyrma, Earth provided exactly that, a brief surge of global heat, a golden opportunity for the journey of a lifetime. The Eocene was a time of climatic instability, punctuated by extreme global warming events, known as hyperthermals triggered by massive releases of carbon into the atmosphere. During these thermal windows lasting only a few thousand years, Arctic temperatures rose high enough for tropical species to migrate northward. This became known as the Bridge and Gate hypothesis, proposed in 2011. Titanomyrma didn't march across a frozen Arctic. It flew across a tropical one. A beautiful, elegant idea, and it quickly became the accepted explanation, until a discovery in Canada sent the story spiraling in a completely new direction. Part 3. The Canadian Surprise and a New Debate. In 2023, a new discovery shook the foundation of that elegant theory. Near the plateau outside Princeton, British Columbia, a local resident unearthed another ant fossil and brought it to the town museum. Scientists, led once again by Bruce Archibald, confirmed it as a Titanomyrma. The problem was its location. Paleobotanical data showed that the Okanagan Highlands during the Eocene had a temperate, much cooler climate than the tropical lowlands, where other Titanomyrma fossils had been found. This was exactly the kind of place that the 2011 hypothesis claimed the heat-loving giants could not survive. It was like finding a polar bear sunbathing in the Sahara. It simply didn't belong there. Or perhaps we've misunderstood the polar bear entirely. And in this case, maybe we've misunderstood the ants. The plot thickened because the Canadian fossil was distorted, making its true size uncertain. That ambiguity ignited a fierce scientific debate with two opposing possibilities. Hypothesis 1. It was small. If the fossil truly represented a smaller ant, it would support the original theory that Titanomyrma species shrank in cooler regions, while their gigantic cousins remained confined to tropical zones. Hypothesis 2. It was large. But if the fossil still belonged to a giant, then our entire understanding of their ecology was wrong. It would mean these ants were far more adaptable than we thought, capable of tolerating a wide range of climates. They wouldn't have needed a brief hyperthermal window to cross the Arctic. They could have done it whenever a land bridge existed. Science isn't a collection of answers, it's a process of asking better questions. And this warped fossil asked the biggest one yet. To understand these ants, perhaps we need to look not at where they died, but how they lived. If you've ever experienced a flying ant day, you know the spectacle skies suddenly filled with swarming insects. It's one of nature's strangest, slightly unsettling events. Now imagine that, but the ants are the size of hummingbirds. In the greenhouse world of the Eocene, life played out on a different scale. With their massive bodies, Titanomyrma may have been formidable predators or scavengers, much like today's army ants, dominating the forest floor and competing with vertebrates for food. But it wasn't the daily toil of workers that granted them immortality in the fossil record. Their eternity came from a single, spectacular event, the greatest mating flight on Earth. Thousands of queens and males took to the air in a frenzied reproductive dance. Most would die a feast for the first insect-eating birds. Only a few lucky ones would mate successfully, and that's why we know them at all. Thousands of queens fell into ancient lakes, sinking into oxygen-poor sediments that preserved them from decay. Each fossil we uncover is a tombstone, a frozen moment from a tragic, magnificent reproductive pilgrimage. But one final question remains. Why be so big? Part 4. Life and legacy of the giants. In our world, size often scales with efficiency. A large truck burns more fuel but carries far more per liter than a car. The same principle holds in nature. In ecology, size is a strategy. In the vast tropical forests of the Eocene, being enormous offered clear advantages. Greater body mass meant more efficient travel across wide territories, helping them locate scarce resources like carrion. It also served as strong defense against medium-sized predators. But there's another counterintuitive advantage. We tend to think larger creatures struggle to shed heat, yet for an insect bigger can actually mean cooler. Just as a large block of ice melts far more slowly than a cube, a giant ant's mass would have buffered it against temperature swings, allowing it to thrive in the volatile warmth of a greenhouse Earth. A larger body has a smaller surface area to volume ratio, meaning it gains and loses heat more slowly. In the superheated world of the Eocene, that ability to regulate temperature and conserve moisture may have been a crucial survival advantage. But Titanomyrma's greatest advantage might have come from what wasn't in its ecosystem. Although birds already existed, the agile, specialized insect eaters we know today had not yet fully evolved. The Eocene represented a unique extreme zone, a brief window in Earth's history, when the climate was warm enough to encourage gigantism, yet aerial predation was not yet strong enough to suppress it. That window closed forever. The story of Titanomyrma is written not only in stone, but also in the pages of scientific journals, a tale of confusion, rediscovery, and the self-correcting nature of human knowledge. It began in 1986, when enormous fossils from Germany were first described under the name Formicium. They were considered natural curiosities, an interesting side branch in the ant family tree. In taxonomy, naming is like issuing a passport. For decades, these giant ants carried the nationality of Formicium. But then, an unexpected immigrant appeared in America, and the authorities had to review all the paperwork. In 2011, the Wyoming specimen changed everything. Recognizing key differences in abdominal shape and other features, Archibald's team created a new genus, Titanomyrma, transferring lots of species into it. They also introduced the compelling thermal corridor hypothesis. And in 2023, the Canadian fossil opened a brand new, controversial chapter. It challenged what we thought we knew and forced scientists back to the drawing board. That is the essence of science, not the search for certainty, but the continual narrowing of uncertainty. The story of Titanomyrma isn't just about an ant. It's a lesson about life on a changing planet. It shows that the existence of any species depends on a delicate intersection of three forces: the evolutionary pressures of its environment, the biomechanical limits of its body, and most importantly, a climatic window that opens just long enough. We often think of gigantism as a burden, a waste of energy, but this story turns that idea on its head. In the superheated world of the Eocene, being giant was a strategy for survival. A larger body regulated temperature and retained water more efficiently. In that long-lost world, bigger meant cooler. 50 million years ago, Titanomyrma seized a fleeting moment when Earth opened a gateway across the icy north and crossed it. So in our own era, as the climate once again changes at breakneck speed, one question lingers. Could there be a species today preparing for the next great evolutionary leap? Leave your thoughts in the comments. Who do you think will be Titanomyrma's heir in the modern world? And if you enjoyed this journey, don't forget to like, share, and subscribe to continue uncovering the buried secrets of Earth's timeline.